I'll take a look at worksheet number 19 now. Questions 5 to 7 that you had for homework over the long weekend. Question number 5 says, we have light with a frequency, not a wavelength, a frequency of 5.5 times 10 to the 14 hertz is shone on a diffraction grating that's scored with 6,000 lines per meter. We talked about this on Thursday. If we have the value of D, the distance between the openings, it would be measured in meters. You really could, we don't usually say this, but you could say it was meters per line or meters per opening. We have now 6,000 lines per meter, not meters per line. Therefore, this isn't D, this is 1 over D. We got to convert that to D in just a moment. That's easy though. The distance from the slits to the screen is 2.5 meters. That's going to be L. We want to find the distance between the second order maximum and the fourth order maximum. That's going to be X. Now, what's the value of N that's consistent with that X? Central maximum, first, second, third, fourth order maximum. We're talking about the second order max and the fourth order max. We're going to say N is equal to 2 here. The equation that we want to use, the one that goes with these givens, is going to be lambda is equal to XD over N times L. We don't know what lambda is though, we don't know what D is. So let's find those first. If F is 5.5 times 10 to the 14, we can find lambda by rearranging the wave equation. It's 3 times 10 to the 8 meters per second, the speed of light, or the speed of any kind of EMR, divided by 5.5 times 10 to the 14 hertz. That gives me a wavelength of 5.4545 times 10 to the negative 7 meters. And D, we're going to find by just simply taking the inverse of 6,000. That gives me a D value of 1.6667 times 10 to the negative 4 meters. Now I can take this equation and rearrange it. X is equal to lambda NL over D. Listen, we want to do our little check to make sure that we're allowed to use this equation. Because we don't know the value of X, it's pretty hard to establish that L is greater than 10 times X. We're just going to have to trust. That's a safe assumption. Whenever they expect you to do a problem with this equation and you don't know the value of X, it is safe to assume that you're under 10 degrees and L is greater than 10 times X, even though you can't actually do the check. So it's okay. If you don't know what X is, go ahead and use the equation anyways. We sub in our numbers here. Lambda was 5.4545 times 10 to the negative 7. N is 2. L is 2.5. And D is 1.6667 times 10 to the negative 4 meters. That gives us the value of X of 1.64 times 10 to the negative 2 meters. Let's have a look at question number 6 now. Same thing, we're given a frequency scored with 5,000 lines per meter. Again, that's not D, that's 1 over D. Here's L. We want to find X this time. When we're measuring the value of X between the second max and the fourth min. Central maximum, first, second, third, fourth order maximum, the second maximum, and the 1, 2, 3, fourth minimum. The difference between 2 and 3.5 is 1.5. So N is 1.5 here. You can find the value of lambda once again by V over F. 3 times 10 to the 8 divided by 6 times 10 to the 14. That's going to give us a value for lambda of 5.00 times 10 to the negative 7 meters. Find the value of D by saying 1 over 5,000. That's going to give me a value of 2.00 times 10 to the negative 4 meters. And then we're going to want to use this equation again. Lambda is equal to XD over N times L. We'd like to do our check, but we can't because we don't know what X is. That's okay. We'll go ahead and do it anyways. Sub in our numbers. X works out to be 7.5 times 10 to the negative 3 meters. And 7, the last one that I asked you to do for homework, This is light with a frequency of 5 times 10 to the 14 hertz. Once again, frequency. Diffraction grating that's scored with 60 lines per centimeter this time. This is 1 over D, but it's in centimeters. We're going to want to convert that. This is L. We want to find X, second order max, and fifth min. Central max, first, second, third, fourth, fifth max, the second order max, and the 1, 2, 3, 4, fifth min. N is going to be the difference between 2 and 4.5 is 2.5. Okay, let's get lambda. Lambda is equal to V over F. Again, it works out to be 6.0 times 10 to the negative 7 meters. D is going to be 1 over 60, which gives me let's say 1.6667 times 10 to the negative 2. This is going to be in centimeters. We want to convert that to meters. It's going to be 1.6667 times 10 to the negative 4 meters. Make sure you flip it over, get the value of D first, and then convert it to meters. We know N is 2.5. Let's use the equation lambda is equal to xd over n times L again. Rearrange that to solve for x. Lambda n L over D. Again, we sub in the numbers that we got. Make sure you use the meters here. When we do that, we get a value for x of 1.8 times 10 to the negative 2 meters. Now, I'd like you to take a look at the last two questions on that worksheet, questions 8 and 9. 9 is going to be a challenge question for you. I want to see what you can do with it, though, after I show you one more little thing. White light is what we call polychromatic light. We've been doing with monochromatic light all this time, one color. All the questions have been almost the same. What happens if we have more than one color? We know that if we have a prism and white light or polychromatic light shines into the prism, then each of the different colors refracts or bends a different amount. Red light has the lowest frequency or the highest wavelength. The index of refraction for that low frequency or high wavelength is the smallest, which causes the smallest frequency, the highest wavelength, to refract the least. Low frequency or high wavelength equals low refraction. But what about diffraction? Different colors will diffract a different amount as well. I want you to take a look at the equation to help us to understand what's happening here. Lambda is equal to d sine theta over n. As lambda increases, then theta will increase. In other words, as the value for lambda is higher or the value for frequency is lower, then the more angle we get, the more spreading out we get. In other words, we're going to say this time low frequencies or high wavelengths, you will get high diffraction. In other words, it's the opposite of refraction. Let me show you what happens in practice here. If we shine red light on a diffraction grating, then we will get an interference pattern that looks like this. Here's my central maximum. On both sides of my central maximum, I get a first order maximum. And on both sides, I get a second order maximum, and so on. If I shine a different color of light, like let's say blue or violet, then we're going to get a different amount of diffraction, a similar interference pattern, but the spacing is going to be different. Remember that blue light has a higher frequency. If we have a higher frequency, we would get more refraction, but if we have a higher frequency, we would get less diffraction. So if I shine blue light here, That would be my central maximum, as it would be for red. But the first order maximum would have a smaller angle than it would for red. The second order maximum, also a smaller angle than for red. So, low frequencies, i.e. red, refract less. Low frequencies diffract more. Now, what happens if I have red and blue together? What happens if I'm shining red light and blue light through this diffraction grating at the same time? Now what happens is that we get these two interference patterns superimposed over one another. This would be our central maximum, n is equal to 0, that is some kind of combination of red and blue light. This would be our first order maximum. We're not saying that this would be first, this would be second, this would be third, this would be fourth. We're saying this blue and this red is our first order maximum. This blue and this red is our second order maximum. Same on the other side. Now, of course, if we had all kinds of other colors, like let's say white light, all the colors of the rainbow, then we would get all of the colors in between the red and the blue. So what you end up here is with multiple spectra. We end up with a spectrum at our first order maximum. We end up at a spectrum at our second order maximum, and on the other side as well. With the prism and refraction, we get one spectrum. One continuous spectrum, a rainbow, one rainbow right here. With the diffraction grating, we get multiple spectra. We get a rainbow at our first order maximum, and then a rainbow at our second order maximum, and so on. What would that central maximum look like? Well, if this was actually white light, then passing through the diffraction grating, then the central maximum would actually be white. It would be all of them because there's no diffraction taking place there. But at the first order maximum, it would be split up like a rainbow. Except, notice the rainbow was backwards. Instead of Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet, it's Dib G. Yor, violet, indigo, and so on. It's backwards. Why? Again, red light refracts the least, red light diffracts the most. Now, realistically, what happens if you get a problem that involves polychromatic light? Don't let it bother you. What I want you to do is pick a color. If you're given data about blue, then pretend the others don't exist. They do, but pretend they don't. If you're given data about red, well, then pretend only red exists. Do the problem like you have all of those other problems, paying attention to only one color, the color for which you have data. All right, now I want you to go back and take a look at those last two questions on the worksheet, questions 8 and 9. Remember, 9 will be a challenge question. Do what you can.